Air quality and SDGs. So air pollution, it is linked with many of the United Nations Sustainable Development Goals. And here you can see SDG with a strong and with or without links to air quality. So the UN Sustainable Development Goal, they have a strong focus on reducing environmental pollution. Specifically, SDG 3.9 seek to substantially reduce the number of deaths and illness from hazardous chemicals and air, water, and soil pollution and contamination by 2030. Effort to combat air pollution will contribute to SDG 3 that I have just mentioned, good health and well-being, SDG target 7.2 on access to clean energy in the homes, and SDG target 11.6 on air quality in city, and SDG target 11.2 on access to sustainable transport, and SDG 13 that is on climate action, as well as the goals of the Paris Agreement on climate change. Now, the economic development, industrialization, and urbanization, basically they led to extremely severe air pollution that causes increasing negative effect on human health, visibility, and climate change. Can you recognize this picture? So this is the picture of the Great Smog of London in 1952. And as the rapid economic development is taking place in the large Asian countries, such as China and India, air pollution is a leading risk factor for environmental public health in these countries. And need not to say, you are realizing the situation in South Asia. However, with economic development, there are opportunities to invest in clean air technologies. So I took some of these pictures from Beijing, New Delhi, Lagos, and Stockholm. And I think you guys may realize the importance of clean air. Exposure to air pollution, it is the world's largest environmental health risk. Reducing air pollution in a given area, it can contribute to improved public health. It can also contribute to longer lives and improved well-being. And the results are measurable in terms of reduced medical expenditure and visible in terms of, the clear and blue skies. Now here, I just want to, give you an idea, about the application or policy messages coming out from an integrated assessment model like Keynes. So here you can see the source apportionment of PM2.5 in Delhi NCT, that is the National Capital Territory of Delhi. And PM2.5 is a fine particulate matter. Okay, it can easily penetrate deep in our lungs and responsible for several problems such as COPD, as well as ULRI, and at the same time stroke and IST and other health problems. So what we did here is that for 2015, the source attribution that quantifies contributions to ambient PM2.5 from different sources is presented in this slide using current legislation in various sectors. And when I talk current legislation, so in 2015, there was Euro 4 in Delhi in that time. That is in the transport sector. Similarly, in the power plants in Delhi, there were ESP 1 or 2 controls there. No FCD was there in that time. So basically, the x-axis, if you look at the x-axis, it distinguishes the spatial origin of PM2.5, where from the PM2.5 is coming. So definitely it is coming from the natural sources. Also, the pollution originated from the long-range transport of emissions from sources in India and outside Delhi, as well as from Punjab, Rajasthan, and neighboring Pakistan. This is the transboundary air pollution. And The third component is coming from emission sources in the surrounding states, Haryana and Uttar Pradesh, and from emissions originating from the city itself, that is the Delhi NCT region. And in the y-axis, I mean, it indicates the amounts originating from emissions of the different economic sectors. And you can see the contribution of, different sectors and subsectors also. So at a traffic hotspot like ITO in Delhi, maybe some of you have seen ITO, the contribution of Delhi NCT, it was 55%, whereas the rest 45% comes from regions outside the immediate jurisdiction of the National Capital Territory of Delhi. And another thing at the sectoral level, if you see here, the dark blue and light blue bars. So you see that the contribution right now, I mean, you can see the contribution, it's approximately 55% is coming from exhaust emissions and 45% is coming from non-exhaust emissions. But in April 2020, I mean, India moved to Euro 6 everywhere across the country. And with, Euro 6 implementation, the contribution of exhaust emissions will go down. And the contribution of non-exhaust emission, that is the road dust, tire wear, brakes, and so on. So the contribution of non-exhaust emissions will increase unless it is controlled. And right now, I don't think there are, any control in non-exhaust emission. Only in few months, like in November, December, when during the high episode, I mean, you can see there is some water sprinkling happening, and that's it. Now, this is the case of, a traffic hotspot. Let us look at the Delhi itself, the whole, National Capital Territory of Delhi. So strikingly, despite the large size of Delhi NCT, with over 18 million inhabitants, I mean, when this study was conducted in 2016, only about 40% of population-weighted exposure to PM2.5 originate from emission sources within the domain. So if the contribution, annual average PM2.5 contribution is 125 microgram per meter cube, that is annual average, okay, please keep in mind. Then only 40% is contributed from Delhi itself, and the 60% of PM2.5 in ambient air in Delhi is transported in the city from outside, out of which about half comes from the surrounding states of Haryana and Uttar Pradesh, 1/4 from even more remote anthropogenic sources, and 1/4 from natural sources. So this kind of results, these are very relevant for the policymakers to understand the contribution of key source sectors and regions. And the results indicates that Delhi NCT, it cannot achieve its clean air target itself. I mean, either it is the National Ambient Air Quality Standard of 40 microgram per meter cube in India, or it is WHO interim target level 1, that is 35 microgram per meter cube. And just imagine, I mean, if we stop all the activities in Delhi, okay, no transport, no cooking, nothing is happening, no electricity use, nothing is happening in Delhi, still it will not be able to achieve National Ambient Air Quality Standards. So therefore, any clean air strategy for Delhi NCT, it will require cooperation with neighboring regions. This is the first outcome. And at the same time, while the power, transport, and industrial sectors were well controlled, it is critically important to look at other region-specific sources, such as the waste management and agriculture and so on. So for example, you can see the significant contribution of secondary particle, the green one. Some of the findings of this study were well taken in the policy process, and a lot of policies implemented after 2016 were focusing on Delhi NCR region. that include part of Uttar Pradesh as well as Haryana. But for such assessment, what is needed? The first thing we need is that emission inventory that include all source sector. I mean, it includes power sector, industrial combustion, industrial processes, transport sector, residential as well as commercial sector, waste and agriculture, and so on. Next, we need, some sort of, ACTM, that is atmospheric chemistry transport model, to assess PM 2.5 concentration. And ultimately cost also, the cost of existing measure. And if you are developing alternative strategies, then you must be aware about the cost of alternative interventions, because for the policymakers, I mean, the cost is really important. I mean, they have limited resource, and within the limited resource, I mean, they want to achieve more and more. So for this, we need an integrated assessment model like GAINS. So what I will do, I will briefly discuss first thing, the integrated assessment modeling, followed by the GAINS model, its methodology, policies, measures, and technologies known as control strategies, emission, cost, and impacts. So as I have already mentioned, that the economic development and air pollution, they are interlinked. So here in the x-axis, you can see the scale of pollution, and in the y-axis, we have economic development. So we have, different scale of air pollution with economic development, from household level to global climate change. So economic development is considered the major driving force of air pollution, and air pollution originates from different sources and at different scale, local to global. Just for example, I mean, if we talk about indoor air pollution in the rural areas of developing countries, it is responsible for over 1.6 million premature deaths each year, particularly in South Asia and in sub-Saharan Africa. And in the urban areas, smog is another serious problem in many cities and continues to harm human health. Similarly, it has a different impact at a regional and global level. But as I said before, at the same time, with economic development, there are opportunities to use clean fuels for cooking, lighting, water heating, and so on, and implement air pollution control technologies in power, industry, transport, etc. Therefore, both air pollution and economic development are interlinked. Now, the basic tenet of the integrated assessment is that air pollution and air pollution control, it is a complex problem that cannot be addressed by a single discipline. It involves many stakeholders and cannot be solved overnight. Here, there is a need for a framework that covers the essential aspect and serve as a platform for communication, such as an integrated assessment model. Now, an assessment is integrated when it presents a broader set of information than is normally derived from a standard research activity. Because integrated assessment, it brings together and summarize information from diverse, field of study. It include, I mean, physicists, meteorologists, I mean, atmospheric chemists, economists, and so on. And they are often used as a tool to help decision makers understand very complex environmental problems. Therefore, the integrated assessment tool, or sometimes it is called IAM, it provides information and it facilitates decisions. And the necessity is that the integrated assessment model, it must provide answer to key policy questions. It must be future oriented, and it facilitates integration of spatial as well as temporal scales. So the objective of an integrated assessment tool is basically to maximize the co-benefits in air quality management as well as greenhouse gas mitigation or other policy priorities. And you can ask, I mean, different questions. For example, why do we bother? Because air pollution and greenhouse gases, they cause serious problem for health, ecosystem, economy, environment, and so on. And what is causing it? For example, eutrophication. It is the result of excess nitrogen deposition. Acidification is the result of excess sulfur deposition, and so on. Now, where is it effective to reduce emissions? In the upwind direction or depend on location and vulnerability of the ecosystem? When can impacts be reduced? I mean, it is very difficult, to reduce the impact. I mean, you have to make, some quick decisions. The way, I mean, they have developed this plan, I mean, for the winters in India. Instantaneous or time scales to be considered. Who has a stake? It's the federal government.
I'm very sorry to interrupt you. Just
Yes.
I have a very basic question. May I ask any question in between, or should I wait for the question and answer session?
There will be, I mean, a question and answer session. So I will appreciate, I mean, you keep your question ready. And once I will, we will go for I mean, before the break, I mean, there will be the time for discussion. Yes.
Right. Many thanks. Thank you. Thank you very much.
Yeah. Now the question is that, I mean, who has a stake? Is it the federal government? Is it the provincial government? Or is it the city administration? Or is it the industry that is causing the pollution? Or is it the consumers? Who should reduce and how much of what? How emissions can be reduced? I mean, it should be end of pipe technologies or switching towards clean fuels. And how much is to be reduced? To be reduced up to the WHO guideline values or the NAQS target of, different countries. So here I have listed, I mean, policy questions for an integrated assessment modeler. I mean, he should be able to respond. So for example, what are the implications of current legislation on future environmental impacts? How far could future impacts be reduced? How much would it cost? How can it be done in the most cost-effective way? Who would have to pay? How much would it cost to reduce air pollution level in a given standard in a country? I mean, if you want to achieve the WHO interim target level 1 in India, how much it will cost? And if you want to achieve WHO target level 2, that is 25 microgram per meter cube, how much it will cost? And is it only for the worst affected areas or everywhere? Now, what is the cheapest way to reduce health impact on the population? Which measures should be taken in which economic sector, which pollutants should be considered in which regions, and which air pollution control maximize the reduction of greenhouse gas emission? It is about the co-benefits. So these kind of policy questions, I mean, you can ask to an integrated assessment modelers, and the IAM must be able to deliver, a justifiable, response. And you can also have, because you guys are working on either as a researcher or working with the ministries and involved in these environmental management issues. So you guys may also have, I mean, your own questions. So here, I just want to show the causal chain. I mean, you can see here the causal chain of the Gaines model. So what is the cause? Because we have the human or anthropogenic activities. I mean, we have transport, we have power generation, we have industrial production, we are cooking, we are heating, we are lightening our houses. So that is responsible for emissions. And once we have emissions, then we can calculate the concentration using some sort of model, atmospheric chemistry transport model. And once you have calculated the concentration, then, for example, for the health impact, you can use the relative risk factors and calculate the health impact. So the GAINS model, I mean, it is an integrated assessment modeling tool that helps to identify smart strategies to protect the local, regional, and global atmosphere while imposing the least burden on economic development. And it is used by the European Union, United Nations Economic Commission for Europe, and various individual countries. For example, we have a separate version for Sweden, Netherlands, Italy, Ireland. China has officially adopted, the GAINS model. Japan and Korea has also adopted the GAINS model. So it is used, I mean, for developing air quality policies, and air quality policies that is cost optimal. And the predecessor of the GAINS model, I mean, that is called the RAINS model, Regional Air Pollution Interaction and Synergies model. It was instrumental in designing important protocol under the Long-Range Transboundary Air Pollution Convention, such as the Second Sulfur Protocol in 1994, Gothenburg Multi-Pollutant and Multi-Effect Protocol in 1999. And in 2012, the GAINS was used for revised, Gothenburg Protocol. And the EASA, I mean, it is designated as EMAP Center for Integrated Assessment Modeling. At the same time, at the EU level, I mean, the GAINS was used for, EU acidification strategy, the NEC directive, and thematic strategy on air pollution and clean air policy packages. And EASA also leads the European Consortium for modeling of air and climate strategies. Now the question is, what is this GAINS model all about? So in principle, I mean, the GAINS model, it is basically a scientific tool to combat air pollution and climate change simultaneously. And around the world, the GAINS system approach, it is framing new policies that maximize co-benefit in air quality management, greenhouse gas mitigation, and other policy priorities. So basically, the GAINS model uses exogenous projections of economic activities. I mean, we take, projections, agricultural projections or energy projections from different, modelers. I mean, it doesn't mean that we are not doing, we also do some sort of modeling within the GAINS itself, but mostly for the, energy activity as well as agricultural projections, we rely on the, exogenous data. And for a given set of, macroeconomic projections and economic activities, the GAINS model is used to assess emissions of 10 air pollutant and 6 greenhouse gases. And as I said that, I mean, in the GAINS model, we convert, policies and measures and standards and regulations relating to, air pollution in a form of control strategy to analyze the impact of current and alternative policy intervention. And as you can see here, there is a cost associated with it. So the GAINS model, it is a big database, huge database, and we have approximately 2000 control measures for air pollutant and greenhouse gases. And as I said, there is a cost associated with each control measures. So once we have calculated the emissions, then we use atmospheric chemistry transport model to assess PM 2.5 concentration and estimate health impact. In the same way, I mean, you can also assess the impact of, VOCs on crop yield and so on. So for a given health and environmental target, this version of the model is available online. Okay, I will come to it later. Okay, so for example, I mean, there is a certain target on health or environment. The policymaker want to reduce, health impact due to air pollution by 50% in 2030. For example, that is your policy target. Then to achieve that policy target, there is an offline version of the model that is the GAINS optimization tool. And it is basically an optimization tool in GAMS code. And this tool is used to identify cost optimal strategies for the given policy target that help decision makers. And as I said that we are using, exogenous projections. So at the global level, I mean, we use exogenous projections provided by IEA. They have, I mean, two models. One is World Energy Outlook model, WEO model, and the second is Energy Technology Perspective model. Okay, there is another global model, I mean, that is called POLS model, and MESSES, that is our in-house model, and the LEAP model from the Stockholm Environmental Institute. So, I mean, we get our, global projections from these models. Then at the regional level, we have PRIMES, I mean, from the University of Athens, and the AIMS model from the NIST, Japan. So the PRIMES model, I mean, its modeling domain is Europe, and AIMS, I mean, its modeling domain is in Asia. And then at the national level. So first I will show the examples from India. So in India, we have, there is a modeling group in Indian Institute of Management at Ahmedabad. So they are our collaborator also. So they use, I mean, the AIMS model. They also use the GCAM model. The GCAM model was developed by this Pacific Northwestern Laboratory, and IIM Ahmedabad, they have developed the Indian version of the GCAM model that is now known as GCAM IIMA, and they also have the Markle model. In TERI, that is one of the think tank here in Delhi, and it is using the Markle model for energy modeling. There is another institute in Delhi, also a think tank, IRADI, and they are using the CGE model. Another think tank in Delhi, CEW, Council on Energy, Environment and Water, they are using the Indian version of the GCAM model. And the NITI Aayog, they have developed, in collaboration with the EASA, they have developed the MESSES IX model. And there is one more think tank based in Bangalore, CSTEP, and they are using the Markle model as well as the TIMES model. In 2017, I mean, the Planning Commission of Pakistan has adopted, NNEO Pakistan model, and they are also able to provide, I mean, national level energy projections, and that is also adopted in Pakistan. So we have our collaborator there, and for Pakistan, we are right now using the NNEO projections. Here you can see the multi-pollutant and multi-effect framework of the GAINS model, and you may notice air pollutant in the horizontal axis and associated impact in the vertical axis. So here we have economic synergies between emission control and multiple benefit. So this dark part, I mean, that was focusing only on criteria air pollutant, PM, SO2, NOx, VOC, and ammonia. It was, included in the RAINS model. And then the RAINS model, it was extended to GAINS, adding, greenhouse gases, 6 Kyoto gases. And later we have also added this NF3. NF3 does not have global coverage at this moment, but it is available for Annex 1 countries. I mean, up to that level, it will take another 2-3 years to implement at the global level. So just see that, I mean, there are multi-pollutant and multi-effect framework. For example, if you reduce SO2, okay, it will also reduce PM, because SO2, when it interacts with ammonia, they form the secondary particulate matter. Similarly, NOx interact with ammonia and they also form secondary PM. Second, if you reduce SO2, then there will be an impact on acidification. And at the same time, there will be an impact on radiative forcing. So SO2 is usually known as, cooling aerosol. I also forget one more thing. When you talk about the PM, then the GAINS model has PM10, we have TSP, we have PM2.5, we have black carbon, and we have organic carbon. And also we have CO, carbon monoxide. And at the same time, I mean, if we reduce NOx emissions, then it will have positive impact not only on life expectancy or premature mortality, but also on acidification, eutrophication, and vegetation. And at the end, I mean, for the policymaker, what is important is that, I mean, they have to weigh that, I mean, what is their target level and how much they can invest, okay? So this is the GAINS air pollution part framework, GAINS framework for the air pollution part. And as I said, we know about the causal chain of air pollution. So anthropogenic activities, they result emission, that result concentration of emission, and accordingly can estimate the associated impact on health, vegetation, and so on. So the key element of the air pollution part of the Gaines model, you can see here, we have economic activities in energy, agriculture, processes, industry, transport, etc. And after implementing the control measure, we can estimate the emissions of air pollutants and their associated health and vegetation impact in terms of, crop loss or something like this. At the same time, one can estimate the cost of environmental control, which we will talk later. Now, what is the criteria of aggregation of emission sources? The Gaines applies basically 5 criteria. One is the importance of a source. I mean, the source must have a contribution more than 0.5% in a country, region, or city. The source, I mean, to the extent possible, there must be a possibility for using uniform activity rates and emission factor. There must be a possibility of establishing plausible forecast of future activity levels. There must be availability and applicability of similar control technologies. And finally, availability of relevant data is critically important. We also need macroeconomic parameters that include population, GDP in market exchange rate, and in purchasing power parity, value added by major sector, for example, the value added by industry, agriculture, and service sector, and transport. And major sectors, they are divided into some subsectors. For example, industrial branches like iron and steel, chemical, mineral products, and so on. And all macro values, they are in constant prices. So we use constant 2015 euro in the Gaines model. I mean, that is in the Gaines 4.0, I mean, in this version. And now coming to this, here you can see the regions in Gaines South Asia. So for South Asia, we have 33 administrative regions. For India, we have 23, Gaines regions. For Bangladesh, we have 2 Gaines regions. One is Dhaka and another is rest of Bangladesh. And for Pakistan, we have 4 Gaines regions. Punjab, Sindh, Karachi is a separate region. And then the Northwest Frontier Province, as well as Balochistan and part of Kashmir, is included in this Northwest Frontier region. For India, I mean, we have usually, I mean, every state is a region, except, the Eastern Himalayan region, that is Arunachal Pradesh, Manipur, the 7 sisters in the Northeast, I mean, they are in the Eastern Himalayan region. And still Telangana is a part of Andhra Pradesh, and Jammu and Kashmir is a one region. But the resolution for Afghanistan, Bhutan, Nepal, and Sri Lanka is at the national level. And just for illustration, I mean, here is the Gaines interface for South Asia. So for the time being, I mean, I will stop here. Now in the Gaines model, I mean, we have 300 plus sectors. And as I have mentioned that, I mean, we have energy, transport, agriculture, processes, industrial combustion, and other sectors. And they are, subdivided into subsectors. So, just imagine, I have shown you the slide of Delhi. And there I have shown you that, okay, basically, I mean, that kind of representation of results is really useful for the policymakers. But to develop that, I mean, we have to start from, the first thing is from emission inventory. Okay, so in the Gaines model, I mean, we have 300 plus sectors. For example, energy, it is divided into power plants, boilers, furnaces, households, refinery. In transport, I mean, we have cars, trucks, buses, 2-stroke and 4-stroke and airships, etc. We have 30 plus sectors there. In agriculture, we have livestock, crop data, fertilizer, grassland, soils. And in the processes, we have, steel, cement, aluminum, brick, fertilizer, and so on. And then we have other solvent related sectors. Having said so, I mean, then how we do the model linkage? Because most of the, if you remember the Gaines slide, I have mentioned that different modeling teams, I mean, they have a resolution either at the global level, or in the global level, they have, either 5 region or 26 region. For example, in IMAIS 3.2, they have 26 regions. In MESSES, they have 5 regions, and so on. But most of the modelers in South Asia, they have a resolution at the national level. They are not, modeling at the state level. Now they have started, but so far, I mean, no one was successful or able to complete, the state level projections. Still, I mean, the modeling teams are working on it. So what we do, we have developed, the GAINS Asia model first with ARRI in China and TERI in India. And they have provided us, based on, their knowledge, the downscaled version of the national level data. And then time to time, I mean, after having several collaborations, we have improved the regional structure. And also from the statistics provided by the government, we have improved the regional structure. And that is called a pattern scenario in GAINS. So as I said that we have, 888 combination of, activities and sectors. So the GAINS model take the national level projection and downscale it at the regional level and sectoral and subsectoral level. So in India, we have 23 regions. We get the national level data and downscale at the subnational level. In China, we have 32 regions. So they provide us the national level data and we divide it at the regional level or provincial level. So this is a slide, from the CDLink project. So usually, I mean, every model, it has a different, way of representing the activities and sectors. Okay, for example, we have final energy consumption in residential and commercial sector. For final energy is basically the electricity, and primary energy is biomass, coal, and so on. But in GAINS, I mean, as I said, for biomass, we have solid biomass and liquid biomass. For coal, we have 6 categories. Okay, based on the coal properties, we have coal, hard coal, we have lignite, and we have the derived coal. For liquids, we have 4 categories. We have, middle distillate, that is diesel. We have gasoline or petrol. We have LPG, and we have heavy fuel. And then they only have one sector at the residential and commercial. But in GAINS, we have residential, commercial, as well as other. And now further in GAINS 4, the residential is divided into rural and urban. And also, I mean, if you go to at the industry level, okay, they provide us data. What is the biomass, coal, gas, liquid, electricity, heat, and other combustion, in industrial sector. But in GAINS, I mean, I just said that this industry sector is further subdivided. So we have pulp and paper, iron and steel, chemical industry, non-ferrous metal, other industry, and so on. Similarly, with the power plant, I mean, we have the existing power plant, we have new plant after 2000, we have advanced plant. I mean, these are the supercritical and ultra supercritical power plant, and we have IGCC plant. We also include the diesel generator sets in the power plant sector if they are being used for electricity generation. If they are being used for, water pumping application, then it goes in domestic other sector, because it include, fuel use in forestry and agriculture and so on. Fuel use in tractors, fuel use in drying, fuel use in water pumping. So it will go in DOM other. Similarly, the transport sector, you can see that, I mean, we have 2-stroke and 4-stroke sources. We have buses, we have light and heavy duty trucks, and so on. So this is the structure of the, GAINS sectors. So having said about, the economic activities, basically about the activities and, sectors, what is the fuel use, that is the activity and sectors. Now we will go about the measures and control strategy. So in different regions and different countries, I mean, there are different policies, for pollution prevention. There could be, some policies at the sectoral level, but here just for the representation, that is known as PM policy. Okay, one of the example I will tell about, the power plant sector. So for example, from the no control, you want to use ESP1, electrostatic precipitator 1 or 2. 2 has the higher removal efficiency or high efficiency deduster. It has 99% removal efficiency, and HED is basically the ESP2 with fabric filter. So for example, you want to implement this kind of technology. So one, you have to provide in the model all the technical parameters. And second, you have to provide the cost parameter. I will come to this later. But the question is that what is a gains control strategy I am talking about? So basically, I mean the gains control strategy, it is a set of numbers or weighted average that tell you for each emission source to what extent which control technology is being applied. So it represents what kind of technologies are used, and it also represents what kind of policies are planned or implemented and how this changes over time. And for each technology, because just imagine about pure PM control in industry, starting from no control to cyclone to ESP1 to HED. And at the same time, in a given region, you could have, in some power plants are using ESP2, but still some power plants are at the ESP1 level. So the sum of the values should not be more than 100%, including no control. So, and total activity, the control is implemented with the activity data. For example, you are talking about the power plant sector. So it is basically the control of the fuel input. And percentage is always relative to activity, and for power plants, activity means energy input. I will give you one example here, and the situation or the understanding will improve based on this. So let us imagine, I mean, there is a region in South Asia, and in that region, the total installed capacity of coal-fired power plant is 800 megawatt electric. So we have 3 power plant. One is large power plant having a capacity of 500 megawatt electric, second one 250 megawatt electric, and third one 50 megawatt electric. Now, the next thing you have to do is that you have to calculate fuel input per year. And for the fuel input, what is needed? We already know about the capacity. We need to know about how many hours, I mean, in a year, the power plant is working. That is usually known as capacity factor or plant load factor. And second thing we know, we should know about the conversion efficiency. So I have already provided, how many hours the power plant is operating in a year and what is the overall, efficiency of the power plant. And based on this, you can easily calculate, what is the fuel input. So for the fuel input, what you have to do, multiply 500 megawatt with 4,000 hours per year, okay? And you will get megawatt hour and convert it in petajoule. And then divide with the overall efficiency, you will get the fuel input of 20.6 petajoule per year. For the first power plant, 6 petajoule per year for second power plant, and 3.4 petajoule per year for the third power plant. Now see, this is one region and it has only 3 coal power plant. Okay, so the coal input is going in power plant, 69% in this power plant, 20% in this power plant, and 11% in this power plant. Now you have to determine control technology in operation. So for example, the first power plant is using FCD. Second power plant is using limestone injection for SO2 control. And in the third power plant, there is no control. So now, I mean, your control strategy is there. Okay. So you have these 3 power plant with different capacity, with different fuel input, and then you have to apply control strategy to the fuel input. Okay. So no control is 11%, limestone injection is 20%, and FGD is 69%. That will be the control strategy for that region. And the sum of all 3 will be 100%. It cannot be more than 100%. And similarly, you can do in, other sectors as well. I mean, in some industry and for different pollutant also. So here, just an example. I mean, this example shows that how the application rate of abatement measures changes with time. And if you are improving the measures, I mean, how it looks like. So in the left, I mean, you can see that in China, in the power sector for SO2 control, I mean, the first policy was using low sulfur coal, and it was started before 2010. And at the same time, they had in-furnace control, means limestone injection. And then they came up with a policy of using FCT, retrofitted, and then they moved to this wet FGD, I mean, with higher efficiency, and now they are using high efficiency flue gas desulfurization. So you can see that with the time, what is happening, that the inefficient technologies are going out and the new technologies with better removal efficiencies are coming. So this is the India's power sector. And in the power sector for PM control, I mean, we have, we have ESP1 that is already as per the policy implemented before 2010. ESP2, it also came, I mean, policies implemented before 2010. So you can see that in 2020, we only have ESP1 and ESP2, but now, I mean, in 2030, you can see that based on the existing as well as planned policies, I mean, we are switching towards HET. And this is the case in Japan about the heavy duty diesel vehicles in the transport sector. So you can see that, I mean, initially they had Euro 1, Euro 2, Euro 3, Euro 4, Euro 5 standards, and now they are moving towards Euro 7. So having discussed, the control strategy, the next is, about the emissions, how we calculate the emissions. So basically, I mean, to calculate the emissions in a no control case, I mean, we just multiplied the activity data with the emission factor and we get our emissions. But if some of the activity data in a given sector or subsector, it is controlled based on the existing policies and plans and regulations, then we can use, I mean, this kind of formula. So, I mean, A is basically the activity data in a given sector, and IJKM, they represent the country, sector, fuel, and abatement technology. EI is basically the emission in a given region or a country. Emission factor, EF, that is basically the raw gas, uncontrolled emission factor or unabated emission factor. And then if you are implementing some technology that is implemented 50%, for example, this is the implementation rate of the considered abatement measure. Then, for example, if you are using FCD, okay, then what is the removal efficiency of SO2 that goes here? So this is the way, I mean, how we calculate the emissions. Now coming to the cost, as I said, that for each control technology or policy measure, there is a cost associated with it. So in the GAINS model, all costs are in economic real term 2005 cost. These are the societal cost. And we are using a standard discount rate of 4% per year. There is sometimes options available if you are, analyzing the cost from the, private perspective. So you can also use 10% or 15% or 20%, discount rate. Taxes are not included because the taxes are transfer payments within a country, and transaction and training costs are also not included. What we include is technology cost, investment cost, operation and maintenance cost, labor cost, and if the technology is using some fuel or electricity, then the cost is included. Non-technical measures, such as behavioral change, I mean, they are not implemented so far as a control technology in the GAINS model, and these are constant over time. Now, mostly, I mean, the costs are, country and technology specific. Now, what are the technology specific factors? Technology specific factors are the investment, fixed operation and maintenance, demand for labor, energy, and byproduct, lifetime of the equipment, and removal efficiency. But just compare, I mean, the labor cost will vary in Austria and Nepal. Okay, so these are the country specific factors. Also, the installation size and plant factors. And sometimes what happened, and this is, I mean, that we have experienced in China and maybe true for South Asia, the removal efficiency of some of the technologies are not as at par, I mean, with the EU legislations. The legislation is same, but due to the, laxed, or not having a proper, annual operation and maintenance, the system, the control technology is not working properly. So instead of 95% removal efficiency, the technology only have 85% removal efficiencies. Other country-specific factors are prices of labor, energy, byproducts. The electricity prices could be different from country to country, and also applicability of the control technology. Because, I mean, if you look at in India, in the old power plants, I mean, there is no possibility of having or implementing FCD. But the new plant that came after 2005, I mean, they have always a space available to implement FCD. So, having discussed about the activities, measures, emissions, and cost part, now coming to the deposition. So, in the GAINS model, I mean, we always deal with annual mean ambient PM2.5 concentration, and it is calculated from emissions of primary PM, SO2, NOx, ammonia, and VOCs. Apart from primary PM, rest are, they form secondary pollutant in the atmosphere. And we use transfer coefficients. There is a linear relationship which describes the influence of emissions of one pollutant from one source region to a grid cell. And grid resolution, it needs to be adequate to the purpose. For example, sometimes in Europe, I mean, we have a very fine resolution, 1 kilometer by 1 kilometer at the street level modeling. But I mean, usually the global version of GAINS, we have, 0.1 degree resolution. And this is one of the example, I mean, of the global GAINS model. This is the, South China Sea. So here you can see the PM2.5 concentration. Okay, and here we have, different grid cells.